Welcome, Math 13 students. I'm going to go ahead and give my lecture for section 9.2, two means independent samples. Before I go ahead and get going, I'm going to note that we only cover two sections out of chapter 9, 9.2 and 9.3. 9.2 is very straightforward and 9.3 is a little bit more subtle. So let me go ahead and begin with 9.2, where we take a look at comparing two means from two distinctly different populations using what we call independent samples. So I will begin by noting that when we sample from two populations, there's a couple of ways we might go about doing it. We're going to begin by looking at what we call independent samples. These are samples that I gather from one population and then from the other population, and there's no real natural pairing or relationship between them. They are not matched in any distinctly unique way. This is what we're going to take a look at in section 9.2. The other type of sampling is when we take a look at what we call dependent samples. Or matched pairs. I'm a particular fan of the matched pairs name because it really says it all. It is two things that are somehow paired or matched. That means there is what we call a natural pairing relationship that exists between the two samples. Simply put, if I know who's in sample number 1, I also know who's in sample number 2. Let me give you an example of both of these. Suppose we wish to compare the earnings of, say, men and women in society at large. I would choose independent samples for this to occur. I go out and I take a sample number 1 from the men and number 2 from the women. I'd have a mean for the 1, I'd have a mean for the 2, and I'd be able to compare them. They wouldn't even have to have the same size. They could be completely different in size. Now, suppose though I wish to compare the earnings of husbands versus wives. These are dependent samples. In the first sample, if hubby's in the first sample, the wife is in the second sample, and vice versa. So if I know one, I know a lot about the other sample. 2 dependent samples. Independent samples, again, this is where we're going to take a look at 9.2 right here, right now. Dependent samples, this will happen in 9.3 in the next lecture. This one's a bit more subtle, but this one that we're going to look at now is very, very straightforward. So we're going to do two things here. In chapter 9, we're going to conduct a test of hypothesis. And we're going to build a confidence interval. What are we going to do this for? We're going to do this for the difference between two populations' means. So we're going to be comparing two population means. We'll have population number 1 over here with mean number 1, and then we'll have population number 2 over here with mean number 2, and we'll be able to compare them. We can conduct a test of hypothesis, or we can build a confidence interval. So, and I want to try to make this as least tedious as possible. At this point in the semester, I want students to realize a couple of things. Number 1, we have a way to do hypothesis tests. It's very technical, but our calculator helps us with that. It's the p-value approach. And if I can find the correct tool, I can set up my test and do that. And realize the same goes for the confidence interval. So a little bit about the notation before we run through an example or two. So remember, I've got two populations. Beginning with population number 1, mu sub 1 is going to be that population mean, unknown, but we are going to compare it with the second population mean. Sigma 1, the standard deviation for that population. And then we get to our sample. From population number 1, we have sample number 1 with its sample size, sample mean, and sample standard deviation. We have the same for the second population. The only difference in the notation is the little number 1 versus the little number 2 for the second population. Now, there are some requirements for building the confidence interval and conducting the test of hypothesis. They are identical, so there's not two lists. It begins where you would expect. We need simple random samples. And the samples for this particular section need to be independent in the in the context I described previously. And then we need either one or both. Both sample sizes need to be greater than 30, or both populations need to be normal. You'll note that this is really the basic list of requirements for using a T distribution. And that's exactly the kind of distribution that we are going to use. So I will note that we're going to use a T distribution to compare the difference between two means. Now, what is not apparent here is because we are really comparing and looking at a difference, we really have but a single population. It's kind of hard to understand and see, but it's the population of differences between samples and between populations. That is truly the population of, of interest. It's not population number 1. It's not population number 2. What we're really looking at is the difference between them. That is the group of items that we are really interested in. Oh, look, it's got a little hat. All right, so there's really but a single population involved in some sense, which is why we use a T distribution, as you're going to see. Now, let's talk about the claims themselves. The null hypothesis. In almost all our tests, I believe we have equality here. And it's really the same as we've said before. We always write that with equality, regardless of the statement less than or equal to, greater than or equal to, or equal to. And then we have the 3 options for the alternative, the less than, the greater than, and the not equal to. And yes, it's left tail, right tail, and two tail. Now, there is a real significant difference. Because there are 2 sets of numbers, the test we use is the 2-sample t-test, and I use that with the p-value method. Now, the real distinction between this material and other material that we've looked at so far is we do not pool our data. Because we've got 2 populations, there is a possibility under some circumstances that we can pool data, but that is a more advanced question. So this semester, we do not pool. And I will show you how we deal with that on our calculator. The calculator enables us via the two-sample t-test to make sure we have the choice to either pool or not pool. So let me talk just a little bit about the confidence interval. There is a point estimate for the difference between the two populations. And the confidence interval looks like this. X bar 1 minus X bar 2. That's the point estimate for the difference. See that? Right there, difference. And we have a confidence interval where we take that point estimate and we add and subtract a margin of error. That margin of error, you can see my t distribution in action there. And you can see that it takes, and it really combines both, in some sense, both the sample 1 data and the sample 2 data. It's worth that to compare with section 7.2, where E was equal to the T alpha over 2 S over the square root of N. But in any case, there we go. Now, I will note that we have the two-sample T interval as the tool of choice here. And my goal here now is to run through an example. This is really a straightforward process. It's important that you don't get overwhelmed by a couple of the formulas in the book. We really will not use them this semester. I'm more interested in teaching the flow of working with this type of material than just about anything else. So let me go ahead and talk about question number 14. This is right out of your text, by the way. It's probably a sign for your homework, but that's all right. We had data on children admitted to intensive care units after vehicle accidents. And some of those children had on seat belts. And then some of those children came from a population that did not have seat belts. All right, so we went out, we got a couple of simple random samples, and we asked, well, in that simple random sample of children that ended up in the ICU, what was the mean number of days spent in the intensive care unit by those children? For the children that wore seatbelts in that sample, there were 123 children in the intensive care unit. Mean length of time was 0.83 days with a standard deviation of 1.77 days. When we get to our second sample, we had 290 children did not have seatbelts on and landed in the intensive care unit. The mean time this group spent in the intensive care unit was 1.39 days with a standard deviation of 3.06 days. So you can see that we've got two distinctly different samples, and we're going to do two things. We're going to test the claim that there is a lower mean time in the ICU for children that were wearing seatbelts when they had their accident. Then we're going to construct the 95% confidence interval for the mean difference between the seatbelt time versus no seatbelt time in the intensive care unit. We'll use a 5% level of significance for the test of hypothesis. That pairs well with the 95% confidence level for the confidence interval. So let me go ahead and run through this in some detail. And we have a claim of lower time for the seat belts. In other words, this mean over here, mean number 1 versus mean number 2, should be less. You'll note that this is a strict inequality, so I've been handed the alternative hypothesis. So I will note that that was mean 1 less than mean 2. This was the seatbelt versus no seatbelt group. All right. So let me go ahead and run through that test. I have my calculator ready to go. So H naught, mu 1, S for seatbelt equals mu 2, S for no seatbelt. The alternative, or let me do that again. I want a little bit more room as I go through this. So, H naught. Mu of seatbelt time is equal to mu of no seatbelt time in the ICU. That means there is really no difference between the two populations. And there we go. There's my alternative. I will also note that this is my initial claim. So now I'm ready to go ahead and find my p-value, and then I'll compare that to my alpha. Let me switch over to my other screen. All right, so we have stat over to test, 2-sample t-test. I have raw statistics, or excuse me, summary statistics. 0.83 days is the mean for the first group. 1.77 days the standard deviation, and 123 is the sample size. 1.39 days for sample number 2. 3.06 days for the standard deviation, and 290 for the sample size. We have a left tail test. It's already selected, and here is where we make our choice about pooling, and we do not pool. There's no reason to actually even change that to yes. Now I can go ahead and calculate. And I have a p-value of 0.01016 or 102, 0.0102. You'll note that it kicks back the data that you've put into your calculator. In case you made some error, you might pick it up there. Notice the degrees of freedom. It's really a weird number. In the previous example, it was n-1, but we got 2 n's here. And one of the complicated formulas is the degree of freedom formula, but my calculator deals with it just fine. So 0.0102. Let me stop my sharing. 0.0102. And 0.0102, 0.05, comfortably less than the level of significance. So we will reject the null hypothesis. So at alpha equals 0.05, data support. Mu of seatbelt less than mu of no seatbelt time. That's my null hypothesis, excuse me, my alternative hypothesis. So 1, 2, 3, 4, 5. Same 5 steps, same basic cake. So it seems clear that if you wear your seatbelt, you're probably going to spend less time in the intensive care unit should you find yourself there. than if you have not worn your seatbelt, or at least if you're a child. Now, let's go ahead and build the 95% confidence interval. And then we'll take a look at those little bits and pieces. So the 95% confidence interval for mu1 minus mu2. So that's what's going to appear in the middle. That'll look like mu1 minus mu2 less than something over here and another value over here. So let me go ahead and share my screen again. One of the nice things about my calculator is it remembers what it's done recently. So when I come over here to stat and I find my 2 sample t interval, look at that, stats. The stats are already in there. In fact, it's even a 95% confident level. And notice, it asked me if I want to pool, and I never jump into this pool. There we go. Now, there's my confidence interval right there. Negative 0.03, and I'm going to take the same rounding as my summary statistics, which is a 2 decimal rounding. So negative 0.03. Negative 1 point. There we go, 0.3 days. Less than mu1 minus mu2, less than at the other end of the scale, negative 0.09 days. All right, so that's what I want to take a look at. Got the numbers I need. Now, a couple of things about my confidence interval. You'll notice that it is a negative confidence interval. In other words, the days here are represented by a negative value. That might be confusing. Why is that? We're comparing the difference between time spent in ICU wearing versus not wearing seatbelts. And it's pretty clear that the seatbelt crowd spent a short time versus the no seatbelts crowd spending a long time. In other words, small minus big equals some sort of negative value. In other words, we spent somewhere between about a tenth and a day less in intensive care. Somewhere in there is the mean difference. My sample statistic, my point estimate, that was a 0.83 minus 1.39. That there is a negative 0.56. So the negative means less days for the seatbelt versus the non-seatbelt crowd. So there we go. We can also do these same problems with the data, raw data, where I need data in list 1 and list 2. But you've seen me do a number of those problems already, so we're going to leave it at that. I'm going to go ahead and stop my recording, and I'll get this posted ASAP. Be well.